All right, so actuators. So any hydraulic system, you have to have a intake filter, a pump or compressor. If it's a compressor, you're dealing with pneumatics. You have to have an intake filter for that as well. By the way, how many of you remember to change the filter in your home about every 2 months? 2 to 3 months. You know why you do that? Yeah, pretty much. You don't want nasty stuff hanging around the area because it can also get into your system and mess it up really badly. So one of the things we can add to these are things like aftercoolers and dryers. With a compressor, a receiver or tank is optional. If you ever go to a job site and they are using pneumatics, 9 times out of 10, they don't have a tank with that. They sit there and they just have this little gas-powered generator. No tank, just goes straight and pressurizes the lines without anything in between it. Pressure regulators are a must. Oilers are nice to have with pneumatics. Again, that just automatically oils everything for you instead of you having to go in and do it yourself. Piping, control valves, all of those are non-optional. An actuator are what do the work. Okay. So two main categories of actuators. You have cylinders, aka linear actuators, and you have rotary, just like the motors we've been using in lab. Okay. You have partial stroke motors, you have full stroke. Those are rotary versus, so the rotary are partial stroke. If any of you have ever messed around with an old rotary phone, did it turn all the way around? No, generally you just took it to whatever number you had to take it to, release and it snaps back, right? That's all it does, kind of like a windshield wiper. So parts of a double acting cylinder. So if I was to deconstruct this double acting cylinder, I should find something pretty similar to this. Okay? So we have wipers, of course. Why do we have wipers? Keep it clean. Because what do you not want inside these? You do not want dirt of any kind. Okay? You do not want dirt getting into these. It would tear it up so fast and you would not ever be able to clean it out. You just have to replace it and it gets costly that way. You have your inlet ports. You have your piston, which is just a solid block of metal. You have seal rings to keep it from leaking from one side to the other. You have the cap end and the head cap, the rod end, and you have indentations for the cylinder to sit back into. We'll talk about those a little bit more here as we go. And of course, those are not labeled. So a double acting cylinder is exactly what it does. Now, we've already talked a little bit about meter in and meter out. Looking at this animation, this kind of can help you explain meter in versus meter out. Meter in is about controlling the airflow in. But because it's controlling the airflow in, it does not control the airflow out. So thus, when pressure is removed and you're adding air over here, it's going to fill it up and push it out. But it's going to have to gain strength behind it because while you might move it, you have all the air behind it to push, really push against it. If you not have the strength, you have to build the strength back here. That's the problem with meter in. Now meter out, whenever you add the air in, meter out, make sure that the volume of air back here is slow to come out while you have the air trying to press in on this side, or on whichever side is currently empty. That is meter in versus meter out. We'll talk about that some more today too. Okay, so meter in versus meter out is almost always connected with a cylinder in order to work with meter in and meter out. That is the fun part of meter in and meter out. Okay. All right, so all right. So cylinders come in all shapes, sizes, and creeds. They are generally dependent as far as size, shape, and everything else. They're dependent on what exactly you need it to do. Because why would you use a double acting cylinder when a single acting with a spring would work just fine? You wouldn't, right? What would you do instead? Take the cheaper option, right? Because the more complex you make something, the more it's going to what? I was thinking the more it costs. Okay. What you have here is a double-ended cylinder. What that means is that mathematically both sides are the rod end, right? And we actually, I think, have one of those over there. Or we did at one point, as far as the show and tell table. Yeah, that particular board's about to go bye-bye because a bunch of people got a hold of some vis-a-vis non-whiteboard friendly markers and decided to write all over it. So that whiteboard won't be around much longer. And then it's a shame because that's a brand new whiteboard. That's actually better than what it used to be because used to it had a bunch of dried marker on there. You can still see a lot of color. All right, so single acting cylinders. Again, they come in all shapes, sizes, and creeds themselves. Why? Because it's always dependent upon the job you're asking them to do. You can have some that are load returned, some that are spring returned. You have rams, you have telescoping. And a lot of these tend to either be brought back by a spring or by the load, not the fluid. I'd love to know how a dump truck's hydraulics work. If those are single acting cylinders that are telescoping, or if probably how that works. Really? Cool. So whenever you remove the fluid from it, it just brings itself back. Okay, well, that's neat. You worked on any of the other big machines? Okay. Mm-hmm.
Pretty much we got your energy from it connects to the drive shaft and it spins the VTO, which causes it to build up the pressure for that build.
Wow. Nice. All right, the single acting cylinders are exactly what they sound like. They use fluid in one direction and remove it so it can return back to normal. You have two piston cylinders. So again, these are all kind of I can't talk today. Okay. All cylinders are chosen based on need. However, these particular ones should be kind of familiar for anybody who's ever worked on their brakes. Because this can actually help clamp brakes. Or anybody have drum brakes? Yeah. So drum brakes work how? They push out, right? It's exactly what these cylinders do. They push out. When you hit the brakes, these engage, they push themselves out, forcing your brake shoe against the drum and forcing everything to stop. That's some old school technology there. The main thing you have to replace, well, no, actually you do, because the metal can wear out, the brakes pads wear out. It's kind of like a brake rotor. Eventually things warp and become in a bad way. So to say that you never replace them is not something I would say. You replace them less often than you do brakes and rotors. How about that? You have to always replace brake pads. You always have to replace rotors periodically. For anybody that doesn't understand why, it's because if the rotor is supposed to be a straight and true piece of metal that you clamp those brakes on, they get kind of warped in any kind of way, or they have buildup in certain places, they don't do so well. Yep. It's always a lot of fun and it is not cheap to get the rotors turned, but sometimes it's cheaper than buying a new rotor. So I digress. Let's move on. All right, so cross section of formed piston rings. So these are just some piston rings that go with the pistons themselves, but that's going to depend upon the shape of the piston as well as the function that they need to be used for. By the way, before we get too much further, piston rings are also can be considered as, anybody know what an O-ring is? It's a seal. That's a lot of what you have to make sure you do with these kind of cylinders, is you have to make sure it seals. And you have to make sure it seals well. The O-ring is probably one of the best ways to seal most things. However, anybody know what was the worst O-ring disaster to ever happen? Challenger. Now I'm talking about the space shuttle. Worst disaster to ever happen was the space shuttle Challenger. It was either Challenger or Discovery. Discovery is the one that crashed more recently, right? Yep, that's the one. So Challenger had a defective O-ring, and that was supposed to seal between the fuel compartment, or the fuel tank rather, and the rockets. Well, it didn't do its job. Well, the whole thing was that the O-ring was not made as one solid piece. It was actually made in pieces and installed later. That's where you had the problem back then. Not to mention, the night before, it had gotten so cold that it had actually, nobody was quite sure if it had done damage. And you have to understand that at the time you had the age of discovery and let's make space travel commercial. Oh, wait, we're doing that now. Huh. So, anyway, I digress on that. So what happened was the O-ring became extremely defective, and instead of calling the launch and saying, no, we don't need to do this, we need to wait, we need to check everything over, they just went ahead and launched it, and we all know what happens from there. So that's why you don't want cracks in your O-ring. It's why you need to inspect your seals frequently, because that's the biggest disaster due to an O-ring. Let's not make another disaster that's smaller. Nah, I hate flying. Not to mention the sheer G-forces. If your body is not physically ready for the G-forces that you have to take to slam yourself out of Earth's atmosphere, you can give yourself some really bad problems. Let's put it this way. They've got all sorts of ways to do it, but at the same time, here's what nobody's quite thought about. Rocket fuel is a hydrocarbon. Everybody wants to talk about, let's save the planet. Well, you know how you save the planet? Set off less rockets. Because you want to talk about something that burns some fossil fuels, you're talking about rockets. The chemical stew that they make in order to set off those rockets is truly some nasty stuff. One problem with that is the fact that if you don't get enough oxygen, especially oxygen going to your brain, I still wouldn't do it. You also have the Dragon Lady, the spy. It's not the spy plane. It's a jet plane that can actually hover above the atmosphere that the military's been using. No, there's another one that's you know which one I'm talking about? Oh, it's not commercial. This is still military, a military plane. I can't remember what it's called. I know the nickname is the Dragon Lady, and I know that it goes up higher than any other aircraft is allowed to go. Not quite, but we'll talk about it later. All right, so and I will say this is most actuators, the linear ones anyway, are screw types. In other words, you screw something on them. Most of the ones I've come across have screws to put it into your system. And that's a good thing. Why? Because it means it can be changed out easily and it can be inspected more easily. It's not as expensive to replace it. However, there are some that you can weld or have pressed, but that means that they're non-repairable because once you weld something, can you unweld it? Nope. It just becomes a hunk of junk, right? And if you do a bad weld, you have some serious problems. And you definitely do not ever want to weld while one of these is under pressure. Can any of you imagine, any of you that have done welding, can you imagine doing a cylinder under pressure? That is not advisable, right? Hmm? I would never trust it. I would never do it. That's why if you're ever going to repair a system, what do you need to make sure you do? Purge it, clear power. What is the term for turning off power and locking it out? Lockout, tag out. It's what you're supposed to do with every system you come across. Why? Because working things live is dangerous and not very bright. Right? But along with lockout, tag out, what should you do? What's another part of lockout, tag out they don't talk about? Always check what you are working with to see if it is locked out. Is that what you mean? So why would we double check it after lockout, tag out? Why don't we just trust that we know what we're doing? There's either stored energy or there's another source of power. So what you should always do after you do lockout, tag out is double check that everything is dead. You go up and you press the buttons, you flip the switches, you do whatever you've got to do. Make sure that power is no longer there. Because you do not want to put your hands on something that still has the power applied. Put it this way, hydraulics lift tons. You put your hands in something that works with hydraulics and it's still live, you're going to lose that hand. You better just say, oh, dear hand, I knew it well, because it will not be attached to your body again. It's going to be flatter than a pancake. Okay? So never, ever work a system live. Always, always make sure it's off and de-energized. So mounting, again, mounting is just as diverse as the cylinders themselves. Most of the time it is designed by the system techs that are looking to sorry. It's designed by the engineers to do what it needs to do and be able to be attached where it needs to be attached so that there is no problem with the clearance or the attachment of these cylinders. Okay. And I can go on and on and on about all the different mounting styles, but like I said, all it ever depends on is where is it going to be put? What is the job it's having to do? That's determined by engineers most of the time, right? Or whoever worked on the machine first. All right. So a lot of cylinders have what are called cushions. So how many of you have ever seen those fast close drawers? The ones where if you try and slam them closed, what do? They slow themselves down and gently pull themselves closed. Y'all know which ones I'm talking about? Mm-hmm. Yeah, a lot of cabinets and stuff like that now have technology to where you cannot slam the door, you cannot slam the drawer. If you try, right before it hits about inch to 2 inch before it's gonna slam into itself. All of a sudden it stops and slows down the force of it before it pulls itself closed. Yeah. So why would we want these on one of these cylinders? So it's not banging back into itself or pulling into itself. Because think about this. Stay. With one of these cylinders, you have pieces of metal inside. What happens when you start banging two pieces of metal together? Not just makes noise, it deforms, and also what else? Have you ever banged two pieces of metal together? You get sparks, which is what is causing the sparks?
Metal on metal contact.
I'm trying not to give you the answer, but I'm going to go ahead and say it. You get little pieces of metal that are flipping out of there. Most of those sparks are teeny little pieces of metal and grit that are just popping off these surfaces. Why? Because you're deforming it, and minor scratches are taking little pieces of metal out of whatever you're banging it on. Okay? That's kind of where I was trying to lead you. Yeah, we're getting close, but not quite there. If you've ever seen, like, if you ever had to bang two pieces of metal together, yes, you do get quite a few sparks, but you also get little bitty slivers of metal that are just jumping off of each other. Most of them are the size of a piece of dust. But what do we not ever want in our cylinders? You don't want anything in there. You want nothing but the fluid that is supposed to be in there. Why? Because this is a very delicate instrument. And if you put a bunch of crap in there that's going to start scratching up the... One of the worst things that can happen is this rod right here ends up getting micro scratches, which don't sound that bad. Except when you start getting more and more micro scratches, what happens to the seal? Oh, the seal's going to become toast, right? And over time, that cylinder becomes useless because it can't seal anymore. Because all that stuff in there is making more and more scratches. Along with that, fluid does not just enter these, it exits as well. So it's going to take all that debris that's in it to other parts of your system, which means that it's scratching up the inside of your walls, of your pipes. It's scratching up the inside of your valves and the seals for those. It's, let's just say, anybody ever use a sandblaster? It does that over time. Which is why we have cushions in a lot of these. So whenever you get to lab, if you try and pull this up all the way too fast, you can hear the air escaping. If you try and slam it back too fast, it does have a cushion of air slowing it down. All of that to say, the whole reason we have those cushions is to make sure it does not slam. Because the slamming of metal to metal does not bode well for your system. It just doesn't. It is a very, very bad thing that at the very least will start damaging everything. At the very worst, it will severely damage everything. Yeah.
So we well, isn't the metal on metal then when we use the little blower
That's external, not internal. External is a different thing altogether, and most of the time those have a little plastic wheel, so you have metal on plastic, not metal on metal. Okay? Yeah. You have metal on plastic, not metal on metal. When you have metal on plastic, not a whole lot of damage tends to occur. Metal on metal does not bode well for any time you ever do it. Ever. If you ever watch Forged in Fire, anybody watch that? Every time they hit that piece of metal trying to beat it out into shape, what flies off? All the pretty sparks and little bits of metal, right? Because they actually will show you that. They sit there and they bang that thing down. They'll do a slow-mo shot, and you can just see little pieces of metal go tingle, and just you have a shimmer in the air from the little bits of metal that are banging off those things. That's the problem about metal on metal. Now, so what we have here is that the fact that the piston creates its own air seal. You have check valves and everything to make sure that this piston cannot bang back hard enough to cause damage. Not to mention, it creates its own cushion of air. And then once it gets past a certain point, that cushion is used up and it just goes back into its normal position. Again, this is how soft closed drawers work and stuff like that. It creates not so much a cushion of air on those, but a mechanical cushion of you can't push it back and it hits like a speed bump and things. I digress. All right, so controlling the speed of an actuator, the time a cylinder will fully extend or retract is determined by the volume of the fluid needed by the cylinder per stroke and the flow rate of the fluid. I will not make you memorize this particular formula. But it is the flow rate formula, huh? No. But let's talk speed. So the volume of the cylinder cannot be changed. The double-acting cylinder with a rod will retract faster than it will extend. Variable displacement rotary actuators, the volume can be changed because of the word variable and the word displacement. Variable means that it varies. The speed of an actuator depends on the flow capabilities of the entire system and the orifice size of the cylinder. Okay. In other words, you have a stadium full of people, the doors are how you get people in and out of the stadium, right? The size of the doors, if you make really, really small doors and space them out quite a bit, it's going to take a while to empty a stadium, right? Versus if you put really big doors in and put them all close together to different parts of the stadium, you can get people out of there pretty quickly. Can't guarantee you that they're going to get out of the parking lot very quickly, but you can get them out of there pretty quick. If you've ever been to the Hoover Met, you know exactly what I'm talking about. That is probably the most disorganized mess that you will ever find. That's where I learned how to drive. All right, so there is a place where you can find estimated cylinder speed. It is in the little white book. Hopefully the bookstore will get some more in soon, but I will go ahead and say this before I forget. Sorry, my ADD is kicking in just a little bit, so go off topic real quick. Well, not completely off topic. So the next time that we have a test, if one of you do not have your book, under online resources. You can't make notes on it. You can't do anything with it, but flip through the pages of it if it'll ever load. It's taking its dear sweet time. Isn't that always the way? When you're in a hurry, everything takes its dear sweet time. When you're waiting for your dinner to cook and you know that's going to take time, all of a sudden the computer rushes through and you're going, wait, what? Slow down. So yes, there is this online. However, the bad downside to it is that you cannot make notes inside it, but it is out there. Circle formula, you have Boyle's law. Force is equal to area times pressure. Oh wait, I have that back there. Torque, hydraulic power flowing, blah, blah, blah. What I love about this little book comes right here. Zoom out just a little bit. All right, so for those of you that have not had a chance to get the book and look through it, one of the favorite pages of mine is page 15. This is where you have hydraulic cylinder force. Now, not all these apply to what you need it to apply to, but enough of these do have answers for you. So the area of, let's say, a 4-inch bore. If you're looking for the area of a 4-inch bore, you have the rod diameter as well. If you're not looking for the rod size, you go with none, and you have 12.567. Now, I will go ahead and say this, these numbers are not always exactly what you need, but they will be in the ballpark. Calculations do vary, but not more than a little bit at a time. So if I look for, again, that same bore, 4-inch bore, but I'm also looking for a 2-inch rod, and I'm looking for the area with that rod, I just follow it across, 9.4254. Another great thing, it gives you PSIs. So if I'm looking for a 4-inch bore, I'm looking for the push force of a 4-inch bore with 750 PSI. 4-inch bore, not worried about the rod. There's my area. There's 500 PSI, and then there's 750 PSI. 94.25. So again, the only thing I don't like about this is the fact that you can't make notes, you can't dog ear it, you can't do anything with it. But if we are having our next test, this is as good as any way to have that little book with you. Okay. And I might even go ahead and say, if you're looking through this book and using it to study, and you want to say, oh, I need to save page 15, I need to save pages 2 and 3, I'm sorry, 3 and 4 for my symbols. Say, look, there's all your symbols, and it breaks it down. Same thing here. Oh, look, there's your actuators for valves. Makes it very easy to do a lot of this, right? So if you want to make notes about what pages you think you might need, that's fine. There's low pressure, there's high pressure ranges, hydraulic cylinder speeds, which is exactly what we're talking about. Okay. This particular one, you're looking at the piston's diameter. You're looking at, are you trying to use the rod side, or are you trying to use just the bore side? Looking at that is how you find your piston speed, because you're also looking at this, gallons per minute. Okay? So you might want to take Thursday while everybody's having fun for Veterans Day and at least take a little time to go over this and make notes of what pages you think you might need for the next test. Yes, tomorrow is Veterans Day. School closed. I think the gates are going to be locked. You come up here, the gates will be locked. However, we will be open for Friday. Huh? Yeah. For those of you that don't, one of the best things you can ever do on your phone, your anything like that, we do have a school calendar and it is up to date. So tomorrow is the 11th and it is Veterans Day, state holiday, campus closed. Oh, happy birthday. If I don't see you between now and then. Yeah, we'll see you Monday. Okay. Anyway, so back to what we're talking about, controlling the speed of an actuator. So yes, we do have that formula. I got myself very off topic just now. All right, controlling the speed. Okay. Controlling speed. The speed of a cylinder is controlled by the flow rate of the fluid actually entering the cylinder and the areas of the piston. Speed of a motor and rotary actuator is controlled by the fluid flow rate entering the motor and the motor's displacement. We generally give that in standard cubic feet per minute. Everybody familiar with that? All right. All right. So speed, some notes on speed. All calculations are estimations. Why? Because well, let me put it this way. Why is the calculation of speed that your car does completely based on? It's looking at rotations per minute. It's looking at the tire that was originally put with the car and the overall diameter of that tire. Because you also have to count in tread and everything else. So I'll put it to you this way. Me being probably shorter than all of you, if you start walking for a mile, it's going to take me a lot longer to walk that same mile. Why? Because I'm a lot shorter than you are, and my stride is not going to be as long. Correct? Okay, now think about what we all do to our vehicles. For those of you that have trucks, how many of you have got spacers or have jacked it up or lowered it down? I've only got one person admitting to it. Okay. That can affect your gas mile. That affects your miles per hour that you're going to see on your speedometer, which is why you really probably want to know exactly how fast you're going at any given point. Anyway, so because you put larger tires, smaller tires, you raise it, you lower it, you have driven the tires till they're bald, or you have fresh tires that just got put on them. All of that affects the speed of your car relative to what you think you're going, right? Well, the same thing is going to affect anything else we deal with. Do we have loss of pressure somewhere, whereby we have an open valve that we don't know about? Do we have maybe a small puncture in a hose that we don't know about where air is escaping? Do we have backflow through any of our pipes that are causing major backups to everything? All of that is going to give you problems with these kind of systems. So we do have losses in a system of hydraulics and pneumatics. We have losses of energy in electricity, HVAC, anything that you can think of. No system is what? No system is perfect. Thank you. No system is ever perfect. Okay? So these less than perfect systems have things like flow loss, and that's going to cause the speed to be varied, right? If somebody messes with a flow control valve, your speed's going to vary. Y'all have all seen that for yourselves as y'all have messed with those flow control valves in lab. So to accurately calculate actuator speed, the actual actuator's inlet flow rate must be used. In other words, you need to know your flow rate into that valve. So what would you have to install? You have to install a flow meter, which those are expensive. They're a pain to install, and you have to install it in such a way that it's probably after the flow control valve. Yep, that sounds about right. Because anything like that's going to be really finicky, isn't it? Yeah. So it's really finicky to try and dial that in just so precisely so that it doesn't end up causing havoc with your cylinders. You don't want it going too fast. You don't want it going too slow. So it's kind of like dialing in a voltage on those trainers we have, right? It takes a minute. Hydraulics. So these are some different cylinder speed estimated. You have velocity is equal. I won't read all these off to y'all because I know y'all can read it for yourself. But you have hydraulics versus pneumatics. The only real difference is with hydraulics, you're going to have to work with gallons per minute. That's dealing with the pump flow rate. In pneumatics, you have actual cubic feet per minute. Full extend and retract time, you have to have the cylinder volumes. What's going to differ between the two is the rod being part of that equation or not being part of the equation. Okay? So any questions on these formulas before we move on? Okay. So flow control circuits. We've talked a little bit about this before, so we're going to kind of talk a little bit about it quickly. So we have meter in, meter out, and bleed off. What is meter in? You control the pressure flowing into your cylinder or your motor or your rotor. What is meter out? You're controlling the pressure out. All right. So going a little deeper into meter in, meter in flow control places the flow between the valve between your pump compressor and the inlet of your actuator. Okay. This is only used for positive loads. In other words, something that we need to push, not pull. I'm sorry. Yeah, that's pretty much right. So only using it for positive loads. It cannot provide accurate control under negative load conditions. And the prime mover is always operating against the maximum pressure setting of the system relief valve. In other words, it takes a lot to make one of these work. So here's a good look at a meter in system. Again, you're controlling the flow in because the flow out goes where? It goes right through your check valve. All right, and on that note, I'm going to go ahead and pause this and let y'all have about a 10-minute break because I can see everybody's getting a little rusty. All right, so meter out. Meter out flow control places the flow control valve between the actuator outlet and the exhaust outlet. It provides accurate control for positive and negative loads, and it's always operating against the maximum pressure setting of the system relief valve. In other words, it's forcing pressure back, it's not allowing it through, so thus you have excessive pressure generally where these things are hanging out. There's a saying when it comes to meter out, and that is when in doubt, meter out, because not only can you control a positive load, in other words, the push of the load, you control the pull of the load too, because whenever it starts towards the negative settings, you can't really move it any faster either way. You have full control of extension and retraction. So basic meter out circuit places the flow control on pressure coming out. Pressure coming in goes straight through the what? What's that symbol? What is this symbol right here? Yes, it is a check valve. Thank you. That is a check valve. All right, so basic flow related circuits. You have another one that's called a bleed off flow control design, where it is placed in a T with the working line between the directional control valve and the actuator inlet. Okay. Measures flow is diverted to the reservoir or exhaust while remaining flow operates the actuator. In other words, this makes it really, really hard to overpressurize your system. Okay? It's a very slow bleed off just to make sure you don't overpressurize your circuit. So design and operation of basic flows related circuits. Bleed off flow control circuit is less accurate than either the meter in or the meter out as to controlling load. Flow is metered back to the reservoir exhaust while the remaining pump output establishes the speed. Remaining flow can vary because of pump efficiency and system leakage. Okay. And under varying flow conditions, it just doesn't work very well. That's why you won't really see it very often. Okay. But it is one of the more energy efficient designs because the prime mover operates at a pressure only high enough to move the load. Any excessive pressure gets to bleed off. All right, so when selecting a cylinder, okay, when we select a cylinder, we don't want to go too big, we don't want to go too little. Anytime you're designing a circuit, it's always about the Goldilocks numbers, right? You don't want to go too big, you don't want to go too little, you want to be just right in the middle, right? So how do you do that? You got to do the math. What kind of force do you need to do the job? You need to add 25% for friction and allow the actuator to move at a reasonable speed. Because, again, no system is what? No system is perfect. I've yet to ever see, hear, or speak to anybody that knows a system that is truly perfect. Look at your car. Is that a perfect system? It is a completely sealed system, is it not? No, even then, you're still going to have loss because you're going to end up burning oil at some point of some place in your engine. So eventually you do have oil loss. Eventually you do have power loss. This is why no system is perfect, because there are so many little bitty finicky variables. You can't possibly do them all. Does that make sense? You need to find out how much pressure will be used and maintained, and divide the required force by the PSI to get the required area. Okay. All right, so there is a formula table right here. So the example they have here is an estimated force is 900 pounds, air pressure is 80 psi. Okay. So we're looking for 80 times whatever power factor we need to get close to 900 pounds. But if you divide 900 by 80, you get 11.25, which is pretty much a 4-inch cylinder, or 4-inch bore. Won't be called on to do this very often, unless you go into the deeper engineering portion of all this. So selecting a valve, it must be able to handle the pressure required by the actuator. It's usually related in CV or KV, which is the flow coefficient. The larger the CV or KV rating, the more fluid the valve can pass. In other words, the bigger the gate, right? Or the bigger the doorway. All right, so here's some valve specs. You can always come back and look at this later. So the CV that is needed depends on the volume of the actuator. So we do this by the area times the stroke of the cylinder. So cylinders all have a stroke. We all define that right there, right? Then you have the constant from table A, which is what is called the pressure drop. We assume the normal pressure drop is 5 psi. So in other words, over the length of the system, we typically drop about 5 psi of pressure. Okay? So for this one, we generally drop 5. FC is compression factor, and time is what it takes for one stroke. So that is how we determine the size of our valves. So we take the area of the cylinder in inches squared, multiply it by the length, we multiply it by our 5 psi compression factor. Okay? We have the 5 compression factor, then we find our 5 psi that goes with it. And the time, divide everything by the time times 29. Don't ask me where they get 29. I don't know. And I have had people ask me, where did they get the 29 from? Some mathematician pulled it out of thin air, and it worked.
Wouldn't it be the same technically? If they just do times 1 for every other thing?
No.
Well, it would not be the same number, but like if they use that for every single, like the formula, no 29 in it, wouldn't it basically be, like, it would still work? It would just be different numbers.
Because you'd have to divide by 29. If you don't multiply by 29, you got to divide by 29.
Well, what I'm saying is, like, if you just got rid of the 29 altogether, like, you never use it, then wouldn't the numbers would be 70%?
No. Because when you divide by 29, it gives you a different number to deal with. I'll give you, we can do one of these.
Well, no, what I'm saying is,
Oh, yeah. Aliens, not so much.
yeah, like, it wouldn't matter.
Again, it's people that did math long before any of us were ever even a thought in somebody's head. Yes.
I think they just added 29.
All right, guys. So page 20 is where we're dealing with this. Where did your pen go? That ate my pen.
Yeah.
Well, the whole thing is that formulaically, if you create a formula, it has to work over every time you use it. Does that make sense?
Well, that's what I'm saying. So if you get rid of the 29,
So, not that kind of pen, hon. Gotta use a blackboard pen. Thank you for trying. Ah, right here. Okay.
it would still be a constant without the 29.
Yes and no. The 29 has to represent something. I just don't know where the number comes from. All right. So let's say we have a 4-inch bore, 2-inch rod, all right, and it takes, we'll say, 30 seconds for extension. Okay. So the area of a 4-inch bore is 12.567. We're going to multiply it by our 2-inch rod. We're not finding the area, we're just using the stroke of the cylinder. I'm sorry, 2-inch rod with a, we'll do a 24-inch stroke. So it'd be 1256 7 times 24. So then we start looking at our FA, which is our compression factor and our pressure drop. Yep.
How is the 4-inch area 12.56? Does it say on page?
Look to page 15 or 16 for your 4-inch bore. Gives you the.
12.56. I got you.
All right. We'll say we're dealing with 60 psi. I'm trying to make this up in my head. I'm sorry. So with 60 psi, that's where we're going to look at this. We have an inlet pressure. When we look at 60 psi, where's my compression factor? Follow it across to what? So I'm going to end up multiplying by 5.1. And I'm looking for my pressure drop. So 60. I'm going to just keep following this over to my 5 psi. Because 5 psi is a constant pressure drop for most applications. It's one that's most commonly used for this, in this particular manner. So follow it all the way across from 60. We found our compression factor. We're looking at our 5 psi pressure drop, which is 0.054. Okay? Then we're going to, once we multiply all this, divide it, excuse me, by 30 times 29. This is how we find the required flow for operating an air cylinder. It literally is required flow for operating an air cylinder. What it is trying to figure out how big a inlet you need in order to allow your cylinder to work as most efficient. So once we multiply all this and then divide by these, so 12.56 times 24 times 5.1 times 0.054 equals 83. Okay. 83.02. We're going to divide that by 30 times 29. So what is 30 times 29? 870. All right. When you divide those out, you get nope. You get 0.095, and that's like I said, that's just to find what size of an inlet you need in order to make everything work correctly with what you've got. Okay. We're going to do another one of these. And I'm going to go ahead and put this formula on the board. You might want to write it down just so that you have it.
This one was in the book on Blackboard.
Yes. Like I said, the book on Blackboard's great if you cannot get the book itself. However, the problem with that is that you can't make any notes, you can't make any corrections or changes or additions to it. Area times length times. All right. So pressure at the inlet, I'm sorry, that needs to be over T times 29. All right.
Like I said, I did order extra of these booklets for everybody.
Okay.
Remember?
So they have ordered extras of
They
those.
ordered it today, yes ma'am.
Okay, good. Hopefully those will come in soon.
I got 10 of them. I don't know if that's enough.
Okay.
They're $1.75.
Yep, $2.
You bought them or bought them?
No, the bookstore buys them.
I bought them from the bookstore, but they didn't have it. So I just ordered it. Whenever they get it in, I'll get up and hang it all up.
Well, in the meantime, we do have the others. All right, so pressure at the inlet to the cylinder is 80 psi when the cylinder is in motion. If not known, use a 5 psi pressure drop. All right, so we use 80 psi, and we have this chart right here. Again, we just look for 80 psi. The compression factor is 6.4, so I'm going to go ahead and bring that down here. My F of A, since we do not know any different, we are going to assume 5 psi, which is 0.048. Okay? Everybody with me so far? For our problem, the cylinder has a 3.5 inch bore and a stroke of 6 inches. So we'll go ahead and put our stroke of 6 inches. And we need the area of our bore, which is 3.5, which would give us what? D squared times 0.785. Those of you that have a calculator. D squared, so 3.5 squared times 0.785 gives you what? It should be 9.62. All right. All right, so then as we are told, we need to extend in 0.75 seconds. We multiply that times 29. Okay? So start multiplying. 9.62 times 6 times 0.048 times 6.4, which gives us 17.73. We're going to divide that by 0.75 times 29, which is 21.75. Divide that out and you should get what?
Yeah, it's gonna be below 1, what do you mean? 17 divided by 21,
Oh, 17, okay. Is there a decimal?
Yeah.
Yeah, yeah. That's a good year, though.
All right, so that should give you 0.815. So you would look for a valve that could give you that number or somewhere close to.
Yeah.
Okay, guys, y'all need to make sure you keep your masks on. Please and thank you. Hmm? You don't got one? Hmm? Yes, please. You're supposed to be wearing one anytime you're indoors and everything else, so. Well, even then, they still wear the masks under that, so tells you how that works.
You can just say you have COPD, so you can technically say you have a medical element that you can't wear a mask for it, and then they can't technically, they're not allowed to ask why or like what you have. But I mean, they can like refuse service, but if they ask, it's like you can like say what they like what you have. If you actually have something like COPD, because you know they can't wear a mask if they have that, because they can't breathe like that well. So like they need as much.
There's all sorts of ways that you can supposedly do something like that, but it doesn't work. Because some places still just have a policy, like the school does, about the masks.
Isn't it weird how that like grocery stores, the workers have to wear them, but the people don't? Like, what's the point of us wearing them?
The point of it is legality. If you get sick, let's say you went to the store and you interacted with an employee that was sick and didn't have their mask on, you can technically turn around and sue that store. Because that is part of the problem with all this is that there's too many different ways that liability factors into this particular disease of COVID. There's really not a lot that it's a virus.
I thought the military was, and a lot of people left.
We're not getting into all that today. We're not getting into all that today. We're going to stay focused on what we need to do. So let's look at cylinder symbols. Again, those are as varied as the cylinders themselves. It always depends upon what. What are your needs? What are you setting up? Okay. Now, I will not insult all of you and your intelligence by going over each one of these. You can come back and look at them yourself. You can kind of take a look at them right now. Again, it's all same thing, varied as anything else. Okay. So this one is particular is a symbol for a rotary actuator. Double acting. So rotary actuators create a force in an arc whose stroke is mechanically limited. So just like a rotary phone, right? You couldn't spin the rotary all the way around. It always snapped back, right? Same thing for rotary actuators. Motors, we've kind of dealt with in lab quite a bit. They convert fluid energy into rotational mechanical energy with an unlimited stroke. Displacement is the amount of fluid, I will not say oil, it is the amount of fluid that must be pumped into a motor to turn it one revolution. Most motors are fixed displacement, however, variable displacements are available. They're either one direction or bidirection. So they either run just one direction perpetually or they have the ability to run the other direction as well. Any questions on that? Okay. So again, more symbols. You can find these in the book. You can find these wherever you think. Hmm. Pretty much kind of how I think it all developed anyway, yeah. Sounds about right. Hydraulic fluid you can't generally see through. Pneumatic, you can see through all day long. Doesn't matter. But, this is how you would select a motor, especially hydraulic one. All of us have had to look at different specs for things and before, yes. How do you pick what you need? You look at the specs you have and you say, oh, this fits my needs. Same thing what you would look at for this. Fluid power motors, you have a gear motor, you have vane motors, you have piston motors. We have a gear motor and a piston motor on this back mechanical trainer. I think at one point we had a vane motor, but I don't know where that one's wandered off to. So if you want to take a look at those while we take a break in a little bit, that's fine. So formulas, you have speed is equal to flow displacement, gallons per minute versus cubic feet per minute, hydraulics versus pneumatics. Horsepower is torque times rotations per minute divided by, again, numbers. I don't know where they get these numbers from. Don't ask. I could not tell you. Somebody with mathematics and engineering in their bloodline said, we're going to use, this is the number that makes the most sense and is the most consistent in how it measures this. So they used the numbers 63025. Where they come up with numbers for mathematical equations, I do not know. So external gear motors, you have two gears that mesh. One gear is connected to the output shaft, one's the input port. And they run like they pair of gears they are. Okay. So you have your input where fluid is moving through. It turns the gears till it moves to the outlet. Okay. It flows through, so it turns the gears till it gets to the outlet and flows out. The system pressure is what moves these gears. All right, you also have internal gear motors. This is where one gear operates inside the other. The inner gear has one less tooth than the outer gear. And you get something that looks a little like this. Your system pressure is still moving your gears. Questions on that? Vane motors, again, work very similar. You're still using system pressure to move things around. That is the purpose of motors, right? Here's another look at that. Vane creates torque due to high inlet pressure on one side and low outlet pressure on the other. So in other words, at one point, at the outlet, it is pulling the fluid out. At the inlet, it's pushing it in. So it makes it just spin to the other side. So kind of like a, I'm trying to think about something that would do a good look at that, but I can't really think of anything off the top of my head right now. Thank you. It's exactly like an old water mill. What makes it move? You put the high pressure at top, it forces the water wheel to turn, dumping it off to the low pressure side, at which point it starts coming back the other way. High pressure moves to low pressure. In that case, I think it was using weight more than anything, since water weighs quite a bit. Pneumatic impact wrench, it's where you can see some of the, you have the rotor cylinder, you have the hammer cage, and all sorts of other fun things. What is good about a impact wrench in pneumatics versus electric? It's way stronger, but what else? You don't have to have a battery on it. Have you ever looked at the inside of an impact wrench whenever you start moving that motor? It creates all sorts of nice little sparky sparks. That's a very bad thing to have in explosive environments. Sparky sparks like to spark off of fumes. Next thing you know, you got a what? You got fire and or a fireball. Something to be careful of, which is why we like pneumatics. Less chance of sparky sparks. Unless you start hitting metal against metal, right? So then we have a piston motor, and we have one of these back there. It's not in its housing like it used to be, but it is kind of neat to look at, and you can spin it, and you can turn it and make it, see what it does. But once again, you're using high pressure that spins to low pressure. All right. That's a really nice looking one on the inside. Inline piston motors. You have piston A, piston B. Everything wants to flow to the exhaust, right? Everything wants to go back to tank. All right. Any questions on what we've covered today? No? If there is one of those, the formula will be given or something like that. For those people that don't have the book. I do need to go back and check test 2 whenever I do some work on these. Okay, so all that being said,